This video is about dot product and cross product of vectors. In order to understand this video, you have to first know about what is vector, how to calculate the magnitude of vector, and also what is determinant. If you have problems with these terms and concepts, you may refer to the YouTube links in the description. We have two types of multiplication for vectors: dot product and cross product. We will first go through some definitions and examples. At the end, there will be some exercise for practice. Now, let's have a look of dot product first. For two non-zero vectors u and v, and theta is the angle between them. The dot product or scalar product of u and v, which is denoted by u dot v, is defined in two ways. Algebraically, it is the summation of all ui and vi, while geometrically, it is the product of the magnitudes of u and v and cosine theta. Here is the proof of u dot v equals to the product of magnitudes of u and v and cosine theta. By cosine law, 2 times the length of vectors u and v times cosine theta can be written as square of length of u plus square of length of v minus square of length of v minus u. After calculations, we get 2 times vector u dot v. Therefore, u dot v equals to the product of magnitudes of u and v and cosine theta. For some special cases, for instance, the vector u and v are parallel. If they are pointed in the same direction, u dot v is simply the product of the magnitudes. If they are in opposite directions, u dot v becomes negative of the product of magnitudes. In particular, if vectors u and v are the same, then we have u dot u equals to the square of its magnitude. Similarly, v dot v equals to the square of its magnitude too. If they are orthogonal, that is perpendicular to each other, their dot product must be 0. For unit vectors I, j, and k, dot product of itself equals to 1, while that of any pairs equals to 0 because they are perpendicular to each other. Here are several properties of dot products. Note that u, v, and w are any vectors, and k is a real number. Now, let's try some examples. Suppose the length of vector A is 4 units and that of B is 1 unit, and the angle between A and B is 60 degrees. The value of A dot B can be found by 4 times 1 times cosine 60 degrees, which equals to 2. Example 2. Given that two vectors A and B, recall that vectors I and j are unit vectors. Part A. Find the value of A dot B. The dot product can be found algebraically, that is 3 times 5 minus 2 times minus 1, which equals to 13. Part B. Hence, find the angle between A and B. First, let theta be the angle required. Then, by change of subject, cosine theta equals to vector A dot vector B over length of A times length of B. After calculation, cosine theta equals to 1 over square root 2. Then theta equals to 45 degrees. Dot product can be applied in 3 areas. The first one is finding the projection of a vector onto another vector. In the figure, suppose C is the foot of perpendicular from B to OA. Then we call vector OC the projection of V on U. The length of vector OC can be found by OB cosine theta, which is the magnitude of V times cosine theta. Since we have learned that U dot V is the length of U times length of V times cosine theta, the magnitude of V times cosine theta, and thus the length of OC equals to U dot V over length of U. As vector OC is in the same direction as vector U, the vector OC can be found by multiplying its length with the unit vector of U. That is U dot V over length of U times U over length of U. The second one is determining the orthogonality of two vectors. Since the dot product of two non-zero vectors is zero, if and only if they are perpendicular to each other or orthogonal. This property can be used to test whether two given vectors are perpendicular to each other or not. The third one is calculating the correlation in statistics. Correlation is the statistical relationship like dependence between two random variables. Suppose x and y are two continuous random variables with mean 0. Their correlation is given by rho x and y equals to the covariance of x and y over the square root of variance x times variance y. As covariance of x and y equals to expectation of xy minus expectation of x times expectation of y, which is x dot y. Variance of x can be written as covariance of x and x, which is expectation of x times x minus square root of expectation of x, which is equals to x dot x. Similarly, the variance of y equals to y dot y. Therefore, the correlation of x and y can be written into x dot y over the square root of x dot x times y dot y. The dot product part ends here. Next, let's talk about cross product. Suppose we have two non-zero vectors u and v in the three-dimensional space. The cross product or vector product of u and v, denoted by u cross v, is the vector which is perpendicular to both vectors u and v. The direction of u cross v is defined by right-hand rule. Vectors u, v, and u cross v always obey the directions as shown in the figure. From the right-hand rule, u cross v is the length of u times length of v times sine theta times the unit vector n, whose direction is defined by the right-hand rule, and its magnitude equals to length of u times length of v times sine theta. Algebraically, if vector u equals to x1i plus y1j plus z1k, and vector v is x2i plus y2j plus z2k, then u cross v can be calculated by this determinant. In case of two parallel vectors, the cross product is 0, no matter the vectors are pointing in same or different direction. For identical vectors, the cross product is also 0. If the two vectors are perpendicular to each other, their cross product is length of u times length of v times unit vector n, while the magnitude of u cross v equals to length of u times length of v. For unit vectors I, j, and k, the cross product of itself is 0. The cross product of any pairs equals to the next vector in any clockwise direction in the figure, and the cross product of any pairs equals to negative of the next vector in the anti-clockwise direction. Here are several properties of cross products. Note that u, v, and w are any vectors, and k is a real number. Now, let's have a look at one example. For two vectors a and b, the cross product can be found by the determinant as shown. After calculation, a cross b equals to minus 10i plus 26j plus 11k. Dot product can be applied into two areas. The first one is calculating the area of parallelogram. From the figure, the area of parallelogram OBCA equals to length of A times length of B times sine theta. That is the magnitude of A cross B. Since the area of triangle OBA is half of that of parallelogram OBCA, the area of triangle OBA can be found by dividing the magnitude of A cross B by half. The second application is the calculation of the volume of parallelopard by scalar triple product. Parallelopard is a prism with all faces are parallelograms. According to the figure, theta is the angle between vectors B and C. Alpha is the angle between vector A and the cross product of B and C. And h is the height of the parallelopard. The volume of parallelopard equals to the base area times height, which is length of B times length of C times sine theta times h. As h equals to the length of A times cosine alpha, the volume then equals to magnitude of B cross C times length of A times cosine alpha, which equals to the magnitude of A dot bracket B cross C. A dot bracket B cross C can be calculated by the determinant shown. Furthermore, if A dot bracket B cross C equals to 0, that means the volume of parallelopard is 0. So vectors A, B, and C are coplanar. That means they are on the same plane. Now, we have finished the tutorial part. Here are some exercises with solutions behind. You may test your understanding of this topic. This is the end of this video. Thank you for watching.